let's say we have an existing structure that we collect the point cloud, we identify the geometry, we have some areas and ideas on the type of structure that is going to, that we want with this. Can we redesign and repurpose this to in a different place in a more optimized fashion? Now, I'm going to be talking about what I mean by optimized, because optimization depends on the criteria that you're going to be placing on that particular, let's say, on what you're trying to optimize for where. And every location, that by itself, or every project, would have certain criteria that is a bit better or more important and a bit less important. And that's where the optimization comes into mind. Can we redesign and optimize this? So essentially, we want to go from the existing structure into an optimal decision or optimized design. And this is very good because now you have some good data that you have for outcomes that you get on one side, and then the types of design on the other side. And this by itself is where, let's say I'm working on to see whether we can train something like a ChatGPT, which is a generative adversarial network, to be able to get designs based on just outcomes. Okay, so let's say your stakeholder has, you know, these safety criteria, this accessibility criteria, this sustainability criteria, this, and then from that we get some initial designs that would more or less with some accuracy satisfy those results. And this by itself will provide us with some information that we can make better decisions. Again, everything that we're talking about is to make better decisions on the other side of it. Okay. Generative facility optimization. I'm also going to talk about what I mean by this, but if we have some data and if we have some, let's say, processes that we have to carry out, we can now again utilize that to make decisions on future facilities as well. Let's say we have a particular type of modular structure that we've modularized it, and we want to build it across different locations. We can now optimize where the locations of the facility sorting or the facility assembly or even the production plants are going to be in order to build this exact modular structure in many different locations. And in this case, I'm giving an example of a static manner, but you can utilize this in a dynamic way to use, let's say, a sequential decision theory and various different types of dynamic decision making to also use time-dependent information that come in as well, and a posterior decision based on information that you're getting at this point or at a later stage, okay? Then I'm going to talk about what do I mean by optimal monitoring plan, earned value management, and project controls, again, using the information that you get from construction projects. And then all of this, you know, fancy, let's say, methodologies to extract these objects from points and pattern recognition, can we use it for other areas as well? And I'm going to give you some examples of physics-informed machine learning and reverse engineering to extract information that we want from each and every one of these topics as well. Okay, so I will talk about two areas in this. One is redesign and reinforcement of dome structures. So I just gave the example of the dome structure just to give you an idea, but the methodology and the process can be implemented in different areas as well. But I just wanted to give you guys some idea. And then the other one is the modularization of a spatial frame or spatial truss in this case, and how we can reuse this if we want to rebuild it in different locations. What can we do? How can we utilize our methodologies, AI-based optimization, to use the information that we get to automatically model our boundary conditions, decision variables, and our objective functions, and then what type of methods we can actually utilize in order to acquire those decision variables based on our optimization criteria and our basically optimization function. Okay, so these types of structures actually exist quite a bit throughout the Middle East and in Tehran as well. And one reason why this actually came to mind for me was because these structures started completely getting destroyed after a few earthquakes that occurred. Now, once these structures exist, if we have a digital model that represents these structures, not only can we rebuild it, we can reinforce it before it actually problems happen, and we can keep the overall shape or let's say the geometry or various different aspects with respect to these structures in different locations. We already are doing that in, let's say, these UN heritage sites, right? But we now have technologies that we can do it in much larger capacities, especially when it has some sentimental value to absolutely each and every one of us, right? So we can keep some of those structures and those geometries. So the idea is this: we have some images. If we were to have a digital model of these with geometry, with dimensions, with various different aspects, we now can reuse this either to rebuild it somewhere else in an optimal way, or to redesign it and optimize it for, let's say, existing but new criteria that we have. As an example, we talked about the serviceability of our infrastructure when the traffic increases. This could also be the load increasing, or let's say, if these are public facilities, the live load increasing. All of these can actually be redesigned there. And the idea was to basically bring it into the mesh structure, which are the spatial structures that we talk about. These are essentially very highly redundant elements that are going to be placed together through nodes and a bunch of elements. And then the area where it's important is how you're going to be placing these geometries to satisfy the conditions that we want in terms of load, in terms of various different aspects as well. So we know that we can actually get from here to here somehow. But we still need to get from here to here. And this is where the automatic as-built model generation becomes important. Using optical metrology, we need to be able, and reality capturing, for instance. In this case, I made an example of a drone taking some pictures of these and then using some automatic methods that I developed to extract the geometry and the locations of each and every one of these domes. Once you have that, then you can actually repurpose that and put it inside of the model. There's, for each of these steps, there's quite a bit of processing that needs to be taken on, carried out. So it's not, let's say, one after the other. The other thing that I would like you to all know is that none of these are scientifically solved. There's a lot of uncertainty that goes inside of getting information from an image or, let's say, point cloud to a digital model, okay? There are methods for particular groups of problems, which we're going to be visiting as well, both in this semester and next semester, that we can get a very good approximation and a very good result at the end. However, this is by no means a solved problem. So I just wanted to give you guys out because it looks nice to get from here to here. But as Frederick knows, last semester we put him through the ringer, I guess, but that's what is going to happen. You need quite a bit of steps here, but it's important for us to know why, because hopefully later on, when you're going to go and find your place in your organizations, you are going to be making decisions as graduates of technology and management in construction to hopefully utilize these technologies, or to be able to basically hire a group of individuals to develop these technologies. So you need to have a good understanding of what the limitations of these technologies are. Okay, generative redesign. Then once you get the geometry, you now can modularize it. Once you modularize it, in this case, I did a simple single layer grid, and you can have different types of, let's say, domes, different types of geometries. There are many different ones that you can use. You can even compare all of them together. But once you have some initial part, then you can actually utilize existing optimization methodologies to get the best option from, let's say, hosts of different options based on your decision variables. So what are all of these jargon words mean? Okay, I'll try to explain. So I simplified the problem. This is actually a geometry of the Dome of Visions in Aarhus in Denmark. Have you guys ever seen it, heard of it? No? So the designer did something very creative. Essentially, this dome You take a look at the diameter. From the center of the dome, go one diameter down, okay? And then project it up into any plane on top of this sphere, okay? This projection is actually a deltile, meaning that equilateral triangles, one after the other. What does this mean? Now we can go and recreate back this by changing the number of these, let's say, elements, the sizes of these, and then we can go reproject it back onto a sphere and get new designs. Why is this important? You're going to be understanding this in lecture 3 when Fayzullah, my assistant, is going to talk about design optimization quite a bit more. Because if we can make it parameterized, which we can right now, because we can actually get a function that could redesign exactly what we have based on only this information here, okay? And based on the location of this as well. If you bring it up or down, it's going to change and create a new design. Then you can now define some decision variables that need to be optimized in order to satisfy some conditions, okay? So in this situation, we have the material type. So I had aluminum, steel, wood. I had the distance here that changed. Based on this, a new design is created. Based on the distances of each and every one of these deltas, also a new design is going to be created, right? Each of these would actually generate a new design. So these would be our decision variables to do what? We want to minimize embodied energy, embodied carbon, weight, volume. So the more traditional approaches are mostly concerned with weight. And if you use one material, the volume would also be the same. But if you're using multiple different materials and you want to find which material is what, then these would differ, right? Because the density of these materials are different. What about embodied energy? Do you guys know what that is? Yeah? Embodied carbon? Any ideas? Yes.
Maybe the carbon produced to use the set structure.
Exactly. Yes. Yes. Same with the energy. Exactly. And there are different definitions of these. And this, hopefully, in your sustainability course, they will go a bit more into the different gated approaches. So, for instance, is it cradle to gate? Is it cradle to grave? Meaning it actually accounts for the amount of carbon that is produced, or hopefully through, let's say, recycling in various different aspects. Once you actually use this material and then basically break it down and demolish the structure, or you want to reuse it somehow. All of these can actually get into the analysis as well. There's quite a bit of huge research just in this area on how you're going to be defining this. I'm just saying that if we define it, we have quite a bit of leeway and quite a bit of opportunities here, right? However, there are some databases that are already there, let's say ICE database, and some of those aspects, we're going to talk about that briefly in this lecture as well. I think you're going to do one assignment that is relevant to that too, if I'm not mistaken. But if not, we're going to be talking about it. But there's whole body of research on how you can accurately utilize this, especially from cradle to grave. That is very challenging. Essentially, from cradle to gate, meaning from the whole production till when you place this material onto the construction project, you would have a good understanding of how that is, because the process is very you can track it back, and you can really calculate some of these as well, or at least get a good estimate of it. But then where the uncertainty really comes is the life cycle analysis of that, okay? But assuming that we have that, if we want to minimize that, then we have a bunch of these, and I think fundamental frequency, we're actually going to maximize it, but we have a bunch of these criteria that, dependent upon different designs, are actually going to give us conflicting results, right? So just think about it. In terms of strain energy, you're going to get this, or in terms of weight, the design that minimizes weight is looking like this. But the design that is minimizing strain energy is actually looking like this. And it makes sense, right? Because you have much more redundancy here. So it's able to just a crude way of thinking of it, a few elements, let's say we remove 5 elements of this versus 5 elements of the other one. Which one is going to collapse more? The other one, right? So this is where you're going to be seeing some conflicting information. And then what we get is here, which is referred to as a Pareto front. Okay, so there are methodologies that we can actually get this Pareto front, and a method that is an AI-based method for multi-objective optimization is called non-sorting dominant genetic algorithm, NSGA2. And then for many objectives, meaning if you have more than, I think, 10, that's where it is, it's the NSGA3. Why am I saying this? Is because it's important for you guys to know that there are methods available, and that's really the main problem for us as construction management students, as technology management and construction students, and as digitization, hopefully in technology graduates, is we need to know that methods exist, but really what is important is how do you model the problem to be able to utilize these methods, okay? So this is where our goal is to bridge these two together. Understand that there are some methods here. What are they? What are some of their let's say, limitations? And then on the other side, you have to still use your traditional or your years experiential information regarding construction management, building science, and various different areas to meet these two together, because any problem needs to be modeled properly, okay? So now this becomes important. Which one of these do we choose? It starts becoming dependent on which one of these criteria and which one of these objectives become more important, right? Because let's say for us, weight is, let's say, many times more important than strain energy. So the final design is going to look more like this than like this, right? Why? Because something has to give. We have multiple different objectives that need to get satisfied, okay? This is where it becomes important, where you have to identify that there is going to be some importance between these multi-objectives, okay? And it turns out that this is much easier to come up with than to say, okay, grade, let's say we know that these are going to be the case. Let's say we sit, in a design charrette or in a let's say a session where we want to decide on which one of these criteria is going to be more important than the other one. And we have different entities that are going to be present to make this decision. This could be from, let's say, the owner side, depends on the project delivery method. I'm not going to even go there, but let's assume that we have some decision-making entities that are there present. How do we approach this? How do we even go and say, well, is it easier for us to come up with which one of these criteria are more important? Or is it easier for us to get an exact number again? Yeah? Any ideas? The first one? Yeah?
A few years ago, it was not that important as it is today, but it was easier to say, okay, weight is more important to us than to embody power.
Yes, it's easier to rank order them rather than put an exact number beside it and say the weight of embodied energy to weight, or let's say to volume, is 2 to 1. And then what we can do here is something interesting, which I use, which is a branch of multi-criteria decision making, is to now use Monte Carlo simulation, which is basically giving a bunch of random numbers that actually satisfy this ordering, and seeing which one of these designs, what percentage of times from all of these designs that our genetic algorithm was able to give us, which one of these designs starts showing itself a bit more, okay? And it turns out we actually end up getting 4 or 5 different designs that gives us a repetitive, let's say, nature to it. So as an example, when we have this type, let's say we have 1,000 different random numbers that we generate that satisfy this. And then we go and we run inside of it from each and every one of these and see which one of these designs were selected based on those numbers and what percentage of that 1,000 times. Okay, so 2.6% was this design, 15.9%, 38.3%, 43, and these two gave us wood, and these two are steel, as an example. Now, this is much easier for us to come up with these four and say, okay, which one do we want? Because given this, there are times that this is going to be good. There are times that this is going to be good. Obviously, this is the majority. If we want to just focus and let's say divert our decision making, transfer our decision making only to the numbers on computers, we can do that. But it's much easier to come up with four or decide on four in a group versus all of these designs, which I think it was 60 or 100, or depends on how much you've set your algorithms to provide you with your Pareto front. So this is the type of decision making also that is important for you guys to understand, that we also, other than the fact that we rely on computers to give us with some numbers, we also have to have some flexibility on how we're going to be using that. Okay. In this case, if we rely 100% on the computer, that's the decision. Okay, go. But what if we want to still play with it? What if we want to still use it, right? Those are the types of areas that also become important, especially when humans are there. Okay, the next one is facility location problem. Okay, let's say that we have some information modeling scheme that we've modularized this in modular components. And then we also have, planned for digital fabrication. This is also sometimes called design for manufacturing and assembly, so that we've designed something that we know based on existing digital fabrication technology, we can build and deliver to the specifications. This could be structural specification, geometry, all of these aspects, okay? This is where the whole area of design for manufacturing and assembly comes in. So let's say we have that, and we want to recreate this in different modular structures. And that's where the capacity comes. Let's say some of them require 50, let's say, columns, some of them require 100 columns, but the assembly and the whole, let's say, building itself is going to be the same, right? Or it's going to use the same principles, or it's going to use the same modules that is going to be taken from existing, let's say, facilities. Now we want to build some facilities so that we can now assemble these or manufacture these or whatever. You can actually have different levels of these. And we want to build exactly this in different locations. I mean, here I put Canada, it could be Europe, it could be anywhere, right? So what do we do? How many of these facilities do we need? Where are the locations? These are all, decision variables, right? We have to make a decision on these. So then we formulate our problem. What we want is the best location and the number of these manufacturing facilities. And I just did one. It could be sorting facilities, let's say, material facilities. You can all have that as well. And this is something that, let's say, Amazon does very well. And they do it on a let's say, a very dynamic way. Okay, but it could be transferred to what we're doing in construction, especially when we're thinking modular. Okay. What do we want? We want to minimize a host of different ones. Say embodied carbon footprint of the transportation of each and every one of these to each and every one of these sites that we have. Okay. Project cost and time, accessibility, various different areas that we have to model, that we want to actually take under consideration, that in our sessions between the stakeholders, we all are in agreement with which ones are important that we need to take under consideration. Okay. So this problem by itself, if we had, let's say, from all of these, let's say, places that we're going to be building this, if we wanted to select, let's say, K of n different locations within these, that by itself was an NP-hard problem. NP-hard is non-polynomial time problem. That means that we do not have any algorithm that could solve this in linear time, okay? So here is where our meta-heuristic methods, like artificial intelligence, AI-based optimizations, like genetic algorithm, particle swarm, these now come in handy. Why? Because it would give us a good solution to a very complex problem. That otherwise, if we wanted to just count all of the possible, let's say, outcomes, it would take forever. But now we have a strategy, dependent upon the type of meta-heuristic algorithm you're using, that is going to be giving you some result. It cannot guarantee that this is going to be the best result, but it can, with some good utility, give you a better result than just randomly picking these. Because now you have some, let's say, idea or some funneling mechanism that would take you towards the best, let's say, objective. And we're going to be talking about that when Faizullah's talks about the genetic algorithm, and I think he's going to talk about particle swarm as well. If not, we're going to talk about it later on in my lectures as well. What it is essentially problems that we cannot deterministically get the objective function. We cannot get the gradient of the objective function. We cannot use classical Newton, Raphson, and let's say, and other methods like that, right? So we have to use some other method. Okay, so then the problem is I wanted to build this into different locations. So the part of this, that tower that we talked about, needs to first be modeled. So you have a point cloud. This by itself is a problem that needs to be solved, right? To automatically extract all of these elements, the locations of these nodes and the elements and all of these need to be identified. Once that is the case, then we have to find a strategy for modularization of these. That means that are there modules that are, let's say, with some definition of module is going to be, let's say, stable and various different aspects that we can take and we can reproduce it in just different dimensions, but it's going to have the same properties, okay? That by itself also needs to be defined and identified. So I created, for instance, a graph-based method and used some topics from frequent subgraph mining to be able to get that sorted. Ends up happening is that you have a bunch of modules that are tetrahedron, and gives you, and this is specific obviously to this problem, but in other problems, you can also utilize it. So now you have an automatic way of getting some modules. Now you have the modules, now you have the problem models, okay? From here, you now have to go and utilize your meta-heuristic algorithms to get the locations and the number of these facilities that you need in order to make this work, okay? So that's where we basically get a bunch of numbers, and these solutions, again, in a similar fashion, gives us with some areas that we can play around with, and they're more or less a bit diverse as well. So some of it has 2, some of it has 7, 3, 5. So we have different, let's say outputs, and we can see based on the criteria that we have and the weight of importance, we have different ones that are there that are ranked a bit better. What this also gives is these capacities here. So right, these numbers here, I don't know if you can see it, I can see it, but there are some numbers beside each and every one of these lines there. What does that mean? That means how many of those modules are going to be supplied to which site, okay? Dependent upon the capacity of that site. So we're optimizing two things at the same time. We're optimizing to know exactly what module is going where, and based on a particular location. That is where it provides us with an opportunity to identify those locations and get some information of the decision variables. Okay? Make sense? Okay. So the whole idea here is if we can model it properly and use technology to automate this process, then we can utilize existing methods from computer science, optimization, and various different areas to be able to make better decisions at the end, okay? So optimal monitoring plan. This is the second one. Let's talk to you about. So this was actually a construction project that I worked on during my PhD. so using basically manual practices to identify the locations of where I'm going to be placing my laser scanner to collect data, I came up with 6 locations that I thought personally, and this was me being an expert of this area, that is going to cover all of these construction sites, right? Can we actually improve that? And turns out we actually can. So this is the final point cloud that I had collected from this. This is after registration. We'll talk about that as well. But let's say that we have a final point cloud based on a set of laser scanner point clouds that we have. Can we actually improve that while still maintaining the integrity, the number of points, the density, and various different areas there as well? So for this problem is minimum number of scan stations, that and their locations to maximize our coverage. Why? Because we want coverage on each and every one of the objects that we have there on site. We want to maximize our precision. That means that the point, let's say, accuracy has to still be maintained. And there are ways to model this. Why? Because just thinking of it, these laser scanners, they basically scan and they emit a signal, it reflects off of that surface. So just think about it. If it's normal to the surface, it comes back very well. But for the same surface, if there's a huge angle, we call it a large incidence angle, that is going to create a problem with the accuracy related to the reflected surface. The more this angle is, the worse it's going to get, actually exponentially. And 60 degrees or more is not good. So we need to put the location in a place where we can minimize those as well, or however way we are going to be defining our precision, and then our registerability, which is a function of our level of overlap. That means that can we actually register the locations of these scans in a way that's without any, let's say, targets or anything else. We're going to talk about that later on as well. But just to give you also some perspective, what I mean by level of coverage, maximum. Oh, and once we have those locations, we can actually use our little friend here to go and collect the data automatically. We can also use a drone or any other number of ways to automate this process. And the automation of this process becomes very important. Why? Because we can actually have frequent data that we're collecting. And the more frequent data we have, the better opportunity we have to define any let's say, discrepancies between our plan and our actual. Okay, so why is level of coverage important? Well, obviously, if we want to have any information about, let's say, a column here about the points there, we need to make sure that that particular column is covered. This is an example. For instance, there are other, let's say, columns that might not be covered. Common sense, for instance, here. If it isn't, then we cannot get any information about it. We don't even know if that column exists or not. We just don't have information about that. We want to minimize that. Doesn't mean that that is going to exist once we're collecting the data on site, but we need to be able to plan that and mitigate the risk of any type of, let's say, issues with respect to coverage. So whatever data that we're collecting, dependent upon the analytics that we want on the other side, needs to be complete. Okay. In this case, coverage becomes important. The other one is level of accuracy. Well, here I have, 5 millimeters, 10 millimeters. I mean, these are a bit high, but let's say if these were in, 6 millimeters, 4 millimeters, 2 millimeters, instead of like an order of magnitude less, the accuracy there. That I can only make that decision if the point cloud is collected in a way that could justify the amount of precision that I'm expecting of it at the end of it. If it's not, then we cannot have it as a basis. So as a rule of thumb, if we want to know whether this particular, let's say, point is in a particular location or not, that by itself has some precision, right? And imprecisions. If this increases, when you're looking at one single point, it could be anywhere in the normal distribution, right? And as that increases, as a standard deviation increases, your certainty reduces, okay? So we want to make sure that we minimize that as well. That's why especially for quality control, the level of accuracy becomes very important. And then the registerability, I'll give you some examples of these. I think it's going to be on lecture 9. But this is an example of me collecting some and giving basically a demonstration of me collecting some images. And using images, you can get point clouds as well. But we're going to talk about that because you need some scale definition and these aspects. But imagine if I'm collecting some images, once I'm doing that through a process called structure from motion, I need each and every one of these images to have some overlap. If they don't, it's kind of like me collecting some images here and then jumping and collecting some images here. If these don't have overlap, they cannot be registered. You can see it here. Okay, so the overlapping of objects, images, or anything else can help quite a bit, especially with automatic registration, because in order to register these together, you need some overlap between them. Okay, so then it turns out that my original plan, which was manual, had 6 scan stations, and this is a registerability map that I created. This means that every one that is basically removed, you can still register the rest of them together. This is a good registerability map. If I only looked at the coverage and did not take on the consideration the level of overlap, I got this, which now gave us 74 surfaces. So I got about 6 more surfaces there, which is good. And I actually came up with 5 scans. So this by itself gave us 24% fewer points if we were to project it backwards and use this map to collect the point clouds instead of what I had planned originally. So this one by itself, other than the fact that it would help with fewer points, which is going to help us with the processing of the data, also it's going to take less time to collect it, right? And it turns out if we actually use the overlap as well, we can actually improve this registerability map as well, while not necessarily impacting any of the benefits with respect to the surfaces as well as to the points. So you have now 32%, which is comparable, but it's still better. But where it really shines is that if this by any chance is blocked on the site, you cannot register these together. These 3 would be registered, but this wouldn't. So if one of these, especially this or this, is blocked, the rest are not going to be registered. In this case, any one that is blocked, the rest would be registered because the overlapping aspect of it is going to be higher. Obviously, if all of them are blocked, then you're going to have a problem. But what this provides is at least a mitigation strategy to improve that aspect, okay? And then we have other methods that we need better modeling to be able to identify that and get some information. Okay, earned value analysis and management and project controls. So this was a construction site that I worked on and collected some data. As basically the construction progressed, I collected some data. This is where I actually gave you that the data from one of these floors that I had collected there. And each and every one of these floors, based on what was progressing, there's a bunch of data that had been collected. From this, once you process this and get all of that information, you're going to get something like this where we can color code it. The color coding is giving us an indication of whether an object, I mean, in this case, I'm putting 2 aspects there. I'm saying that if it's green, it's on schedule. That means that I can observe this, let's say, column, and this column is actually within the tolerances for our quality of what we expect from a column to be, okay? If it's red, that means that it's behind schedule. That means that it doesn't exist. If it's yellow, that means it does exist, but it just doesn't meet the quality standards for our tolerances. Using this, we can now get something. So this is a good, let's say, identification of, well, you know, this is our project, right? If these are, let's say, red or you know, how it is, we can get some information on how this project is going to be. Some of them, I might say that, you know, I might get a different color there to say ahead of schedule, right? So if you have a bunch of these that are ahead of schedule, behind schedule, we can get a good visualization here. But typically in our analytics, we want a good, nice number for our descriptive analytics, right? And this is one way that we have what we call the project controls is through earned value analysis. Are you guys familiar with earned value analysis? Have you, no, you haven't heard of it in your undergrads? We're going to talk about this briefly as well. Essentially, it gives you an earned value in terms of units of cost versus your planned value, which was what was planned based on what was expected to be completed versus what has actually been completed. It's a very popular project controls method because it just gives you a bunch of numbers and gives you the schedule slippages and various different aspects there as well. You can just observe it and you can know, okay, we're not doing as good. We're not doing as good. You're doing a bit better, but still we're behind. Meaning that the gap between these have reduced, but it's still a gap, right? So now in terms of a stakeholder, you can take a look at it and really say, okay, there are some problems. This is a type of what we call a descriptive analytic, meaning that we can actually describe it and visualize it and observe the data as it is. So essentially, all of these collecting of this, analyzing it, make it into a color coding, and then reflecting it into an existing system, all of these need to occur in an automated fashion for this to actually make any type of sense, right? At the end, we want to get from this to this. Make sense? Yeah? Okay. So what do we need to accomplish here? So I give some examples of automatic alignment. So I have created some nice, let's say, methods to be able to automatically align these two together. So you have a model and then you have a point cloud that you can assume that is registered because you can actually register the point clouds together through overlaps and through targets. But in order to register it with the model, you need some more, let's say, sophisticated ways of doing that. So I have a method that I use through particle swarm. I mean, you can select what those methods are and how you're going to be doing it. I'll give a demonstration. What the method does is basically it takes the orientated point cloud and it goes and it estimates. And the estimation part is only for demonstration purposes so that we can estimate what we call the normal to every surface. So imagine you have a bunch of points that represent this surrounding surface. So you now need to provide some representation of this, okay? Let's say the majority of these points are going to be, the normal is going to be the plane of the ceiling, the floor, the sides, yeah, and the other sides. This by itself shows itself here in the normal estimation. So if we take for every point a neighborhood around it and get the surface normal of that, basically fit a plane to that. Similar to fitting a line in 2D, we fit a plane in 3D, okay? We now get a bunch of, let's say, peaks that could be possible peaks for the locations of our three main coordinates. These are for rectilinear structures. Now, based on all of these are the best practices in computer science and kernel, basically, definitions. You still get some of these peaks that are not going to be significant. Now you have to think about a strategy that differentiates between the significant peaks and the others so that you can adjust these two together. That's where this whole point was. Once you do that, for every dimension, you use some AI-based method. In this case, I'm just giving a demonstration of particle swarm, but I have some others as well. And then from that, it basically starts optimizing it. Once it optimizes, it basically goes and moves it together as well. So in this strategy, I employ the way of first orientating this and making it into the three proper orthogonal directions, and then solving the translation problem based on that. There are different methods that you can utilize, but I just wanted to give you an idea of the fact that it is not a simple, trivial aspect, okay? And automating each of these parts becomes important to actually use the information that we want. really the collection of the point cloud, all of the aspects related to it becomes important. Why? Because it's actually a non-tool time activity. Do we know what a non-tool time activity is? It's a non-production activity, right? No one is paying you to collect to see if you're doing well or not, right? You need these analytics in order to make certain decisions. But in reality, it's a non-production activity. You're not giving it as a progress report, right? So if we can actually minimize this, that decision makers need, the time that it takes to do that through automation, we need it frequently, the decision makers need it, and it's really non-production activity. So it's a perfect prime example for automation. That's why we're really doing this. Okay. And then once we have that, then what we can do is for each and every one of these elements, we can go and essentially collect those elements. And then I do a boundary outside of every element of the model that I want to detect. Then once I identify those boundaries, then I go and use some methodologies that I've developed in order to get these two essentially register together to see how much they're actually far apart from each other. This is where we can get the dimensional compliance there. So this is essentially a model fitting. You're fitting a model of what the model was versus what the points that are on its surrounding there. And then based on that, you can say, okay, the final RMSE, what does that mean? That means that once this set of points are fitted to that model, that's how accurate it is. It's within, in this case, 0.007 millimeters. But the total error in this case is a bit more, right? And other aspects of it as well, in order of magnitude more. Let's see. And then here, I think I show it. So in this case, for instance, I think this is 3 centimeters. I apologize. I think this is not in millimeters. This is in meters. But what it is that it could give you what the total error from what the final version is to what it used to be in the beginning. How much did it need to move? And then this here gives us how well we've actually fit our model, which as long as it's within the precision and the random measurement error of our instrument, we're good. In this case, for instance, it's 3 millimeters. 3 millimeters is more or less within the boundaries of what we can expect from a point cloud that we collect from laser scanners. And then in this case, for instance, you can see it's 28 centimeters, for instance, the difference between them. But the final model is within 5 millimeters. So that's good. That means that the model has been fit properly. The dimensions of this is good, but the placement of this object is not. Make sense? So you get some information related to that. Okay, so how can we use some of this information for reverse engineering? This was another construction site that I collected some data from. Essentially what this is, a cantilever beam truss. Cantilevers are basically, they have no supports on one side. So, and this was a long, I think, 20-something meter cantilever truss. And you can see here that there are some temporary bracings, right? Essentially, we wanted to see how much this displacement is once this temporary bracing is removed. So it looks like this. Why is this important? Obviously, for structural responses, this is very important because this is going to be a public facility. Live load becomes an important aspect related to that. There are some windows that were installed on the outside of it, that these are prefabricated windows. If the structural response in this case does not match what was supposed to be matched, then we would know that this is even going to come down further. So this only gives us some indication, and then the other dead loads also gives us some additional indications. Are we within the boundaries that we want, or is this going to just go up and down like this? Because this is a long cantilever, okay? So, and this is going to be the finished product, which is a bunch of, let's say, dead loads that are going to come on top of it. So here was the time that we needed a very fast method of finding out how much this is coming down. And by means of identifying how much this is coming down, we can then identify different aspects. So I'll give an example here. What was important for us, and I don't know how many of you guys have a structural engineering background or you've taken structural analysis in your undergrad. Yeah. So you're familiar with the stiffness matrix. Yeah. Finite element modeling stiffness matrix. Essentially, how stiff your structure is. You know, this is like if you want to compare it with the Young's modulus in terms of material, that means that how much do we want to pressure a material or put it in tension, and how much that particular displacement is. The resistance there is that stiffness matrix. Okay, so this now provides us with some indication of how the structure is going to behave. Now, each and every one of these joints, I can tell you that has been planned to have 100% fixity. Do we know what fixity is? That means that every bit of the moment that is there is going to be transferred. Is that really true? Probably not, right? I mean, that's a good guess. But we want to make sure. We want to have actual real world experimentation to know. In this case, fixity became important for them and for the contractor. In some other cases, we might have laboratory, let's say, testing of the fixity factors prior to that. And if we have that, that would be fine. In this case, because this was a very unique structure, they had single joint testing, but not as an entirety. So what do we have? We have these displacements. We can now back calculate it, and for each and every one of them, actually estimate these fixity factors. What does that provide? That provides us with now a basis of our stiffness matrix that we're going to be utilizing to be able to, again, simulate what is going to happen afterwards. And this is a combination of what we call a physics-informed machine learning procedure. In this case, we can actually circumvent the machine learning side by using AI-based optimization. But in many other cases, when you have dynamic loading, you need good and fast predictions of these. So you can always use these high-fidelity models, finite element models, to be able to train these neural networks to give you some good predictions, some fast and good predictions. This way, as you have a dynamic, let's say, load that is going to be passing your infrastructure, you would have a good, let's say, hourly or let's say daily information about what those load changes and what those displacements are, and does it actually comply with what you would get from reality through the strain gauges. And if these two don't match, then we're going to have to look a bit deeper into it and have other types of analytics, okay? So anything that we're doing has to serve some purpose, okay? Okay, so how do we actually solve this? We have all of these different elements. So for this, I had to create some interesting methods. And one was, can I actually just use any type of shape that I have on my let's say model and the digital model, and create a function for that shape, and then fit that shape directly to a point cloud that is surrounding it, and seeing where I end up. Because the finite element model, even if I have a very, very accurate one, it likely is not going to match what I had. So if I just use distance of point to the model, it's not going to give me anything, okay? So I had to come up with some solutions. So this was one of those solutions. So I get any type of shape. I approximated using Fourier series. We call it trigonometric polynomial. So a bunch of cosines and sines. This turns out to be one of the most parsimonious models. That means that it's a short-term form. It's very good because it's continuous. Now I've basically summarized a non-parametrical shape in a continuous function. And now I can use our traditional model fitting methods like Newton-Raphson method as an example. This way, because I've made it continuous, now it has the objective function has a gradient. So I just wanted to give you the idea of why this becomes a bit more important, because it doesn't look, it's like, well, we can use this, we can use this, we can use whatever. No, it turns out being it simplifies the problem quite a bit. And then I added to a meta-heuristic algorithm that takes any type of orientation there and shifts it back to the original orientation. And then from there, I can use a robust model fitting to extract the points that are surrounding it. I'll give a demonstration of an app that I developed for this. So give a very exaggerated orientation. These are the points of this, and this is the model. My aim is to move this in a way or perform model fitting so that these two start aligning. So I use, again, I use particle swarm in this case, but you can use genetic algorithm and other aspects as well. And it starts converging. So what does this convergence mean? You have a bunch of numbers that it basically starts taking, and then it starts funneling them and finding the best ones. Really where the mean particle score and the best one starts getting close together, that's where the method starts converging. That's really when you know the method cannot provide you anything better. So it came from this, it got from this to this. This does not look at all like an I-shaped member, but it orientated it to basically get that. And then from that, we do another extra step. And at the end, we get some information about that as well on what the orientation and various different aspects. Once we have that in a very exaggerated way, any type of displacement there, we can actually start accounting for it. And then we can use that to get the actual model from this particular element. So you have a bunch of these elements together. We basically intersect these elements and get those, let's say, in this case, nodes and elements together, and then identify what we want. Make sense?